In today's video, we're going to be talking about the boundary behavior that goes on with light when changing from one medium to another medium. So after watching this video, you should be able to tell me what refraction is and what actually causes it. So let's get right to the good stuff. The refraction of light waves. Basically what ends up happening is when light hits a new medium, and what I mean by that is when light changes from, say, like air to water, or from water to air, or from air into glass, a few things happen, and they're listed here. A portion of the light wave will reflect off of the boundary, and a portion of it will enter the new medium, and that's really what we're concerned with, is this portion that enters the new medium. What happens to that light wave as it goes into this new substance, okay? And a few things that happen is the wavelength changes, okay, and that's represented by lambda. The wavelength would change. The speed changes. The light bends in some way, shape, or form, but the frequency does not change. Okay, and I use this kind of catchy phrase, I guess. Red in air is red underwater, because the frequency of light is what determines the color that it produces, and that will not change when it's entering into a new medium. So if we look at this formula that we've been dealing with in the previous chapters, V equals frequency times lambda, which is wavelength. All right, the things that will change when entering a new medium is the velocity. Okay, it can go up or down, and the wavelength, it can go up and down. And what you're going to find is that these lambda and velocity are directly related. So as velocity increases, wavelength increases. As velocity decreases, wavelength decreases. But one thing that is constant and does not change would be the frequency of the wave itself. Okay, that does not change. So this bending of the path of light is known as refraction. Right? The bending of light is known as refraction. So here's a picture of refraction. Here we have this red line is supposed to indicate a light wave, and it's headed in some medium. What we can assume that this, we'll say it's air. Okay, it's headed in air. Okay, and then it enters into a new medium, and we'll say that it is we'll call it water. Kind of looks like water, I guess. Okay, these black lines are supposed to represent the wavelengths. Okay, so here you can see that we have a longer wavelength compared to, say, here. Okay, and if we have a longer wavelength, we have a higher velocity. So the speed at which this light wave is moving in this medium is faster than, say, the speed that's moving in this medium. Okay, and you can see as soon as this light wave hits this boundary, the boundary between the air and water, you have some bending going on, and that bending is called refraction. So an electromagnetic wave, which can include a light wave, but it also includes other things like radio waves, microwaves, and all that, X-rays, all that good stuff. An electromagnetic wave is produced by a vibrating electric charge. And really, electromagnetic waves, all the stuff that goes on with them is way beyond the scope of this course. So just kind of take my word for it that it's a vibrating electric charge. And as that wave moves through the vacuum of empty space, it travels at a constant speed of 3 times 10 to the 8th meters per second. Okay, that is the velocity of light in a vacuum. And as far as we know, nothing can travel faster than this speed. Okay, this is called the speed of light. So when you hear that term, the speed of light, that's what they're talking about there, 3 times 10 to the 8th meters per second. And that's pretty dang fast, okay? And like I said, as far as we know, we don't know of anything that can go faster than that. And we give it a special symbol, and that is c. Okay, the speed of light is represented by the symbol c. Now, the speed of light can go slower than 3 times 10 to the 8th meters per second. And the way that that can happen is if it travels in a different medium than, say, a vacuum. So for instance, light does travel a little bit slower in our atmosphere, in the air, because basically the air has this thing called optical density. And basically what it's saying is the amount of stuff in this material will slow the speed of this light wave down. Okay, so air makes light travel a little bit slower, and light travels even a little bit slower, say like in water. Okay, and light travels slower in glass, and it just depends on the material, but it's going to determine the speed at which that wave travels, and that is due to the optical density of the material. Okay, it has nothing to do with the optical density of, say, the light itself. Okay, because light doesn't have like mass, but it depends upon the material that it's traveling through. So that leads me to this thing called the index of refraction. Okay, and the index of refraction is basically a value, okay, represented by the symbol n. Okay, n. And it's a value that expresses the relative speed of light in a vacuum compared to the speed of light in whatever material it is. And so I have here V material, and that material could be air, it could be water, it could be whatever, glass, you name it. Okay, so the top number is the speed of light in a vacuum, and the bottom number would be the speed of the wave. It doesn't have to be light per se, but the speed of the wave in whatever material it is. And if you take this ratio, if you will, you can then get the n value. And this n value, the lowest it can be is 1, okay, which would basically be light's traveling in a vacuum. Because if you take 3 times 10 to the 8th meters per second divided by 3 times 10 to the 8th meters per second, that would be 1. And as you go up from there, the speed of the light wave, or the wave itself, I should say, gets slower. So if you have an n value of, say, like 3, that's going to be considerably slower than, say, an n value of 1.5 or something like that. Okay, so that's the index of refraction. So the tendency of a ray of light to bend one direction or another is dependent upon whether the light wave speeds up or slows down when crossing a boundary. Okay, so in this picture, we have a light wave which is represented by blue, and it hits this boundary, which is glass, and you can see it starts to bend. Okay, and that, again, that is called refraction. And the direction of that bending is kind of important, and that's something that we're going to be interested in learning about or talking about. So I've got some ways to help you remember what direction light waves bend, and we'll talk about that in just a second. So here, I'm talking about when a wave enters a new medium, it will travel at a new speed. Okay, we know that. We talked about that in the previous slide. In order to keep the same frequency, the wavelength must change. Remember, frequency does not change, okay? If it goes from a fast medium to a slow one, so here, this is supposed to represent a light wave. I'll try to draw it in here. A light wave traveling down this direction, okay, traveling down this direction. And these black lines are supposed to represent the wavelength, if you will. It's kind of like you're looking down, you're seeing this wavelength of the light wave. If it goes from a fast medium to a slow one, from top to bottom, the wavelength gets smaller, and the speed of the wave slows. So it slows down, and the wavelength gets smaller. Okay, and you can see that happening here. Here, look at the wavelength. We'll call this like x, right? Whatever that is. And then if you look at the wavelength here, it looks like almost half, right? So we call that like x over 2. The wavelength has considerably gotten smaller. Okay, and also what we can say down here is this is much slower than, say, up here where it's much faster. Okay, so the speed and the wavelength has decreased. Okay, so what happens to this bending as light travels from I'm going to do an example, from a fast medium to a slow medium? Okay, and I'll do the opposite in the next slide. Okay, so if light travels from a fast medium to a slow medium, what ends up happening? Okay, what ends up happening is basically the light ray bends towards the normal. Okay, and you may say, well, what's the normal? The normal is just basically a line that is perpendicular to the boundary. Okay, so I'm going to say that this is a piece of glass. Okay. And then on this other, and here's the boundary right here, this line, and on this side we'll call it air. Okay, and this is the boundary right here. The normal would just be a line that extends perpendicular to this boundary. Okay, so however it's positioned, it would just be perpendicular to that boundary. Okay, and basically my rule says that if you go from a fast medium to a slower medium, the light wave bends towards the normal. Okay, and I'm going to use a different color here just to kind of keep things a little bit clearer. So here is my light ray. All right, and that should be a straight line, even though it's not really. Okay, so it's going this way. It's coming in, entering into the glass. Okay, it hits the glass boundary, and now it's going to diffract. What direction is it going to diffract? Left or right? Well, according to my rule, it says it's going to bend towards the normal. Okay, and so you would have a slight bend this direction. Okay, so you can see that it has diffracted. So it was going straight into the glass, and now it's bent towards the normal. Okay, and this may be a helpful mnemonic device for you. FST, okay, and it sounds kind of like fast. Okay, and that's fast to slow. And basically, what FST stands for is fast to slow towards normal. Okay, so this F is supposed to, I believe, represent the fast. The S is supposed to be the slow, and then T towards. If that's helpful to you, great. You know, I mean, that might be what you write down in your index card for, say, a test or something like that. But FST, fast to slow towards normal. All right. Let's do the opposite of what we were just doing in the previous slide. Let's say we have a light ray that's going from a slow medium to a fast medium. What happens there? Okay, so again, we'll call this glass, and I'll call this air down here. Okay, and I'm going to draw my normal line. There it is. Okay, and basically we have a light ray that is let's see here, we'll use injective, that is coming from the slow medium, so it's starting in the glass. It's headed from the glass. Okay, and it hits this boundary between the glass and the air, and it says that the light ray will bend away from the normal line, okay, away from this line. So instead here, instead of heading this direction towards the normal, it's actually going to bend away. It's going to bend something like that, okay? And if you're looking for a mnemonic device, here you have it, SFA, slow to fast, bends away from the normal. Okay. And you may be saying, well, how much does it bend away from the normal? Well, that's a great question. That is what lesson 2 will be about. We're going to figure out these angles that it bends away from the normal. Okay, so hang tight. Just for right now, though, kind of keep it more conceptual, if you will, and just keep these little mnemonic devices in mind. One more thing just to kind of show you guys I think is kind of cool. This is a piece of lucite, which is just glass, basically. Okay, and then outside here we have air on either side of this glass cube. Okay, and a laser is being shot through this piece of lucite. And here you can see that this is where you have, it's fast outside, like a fast medium. This is slow, and this is fast. Okay, and how do I know that? How do I know that the lucite isn't actually faster than, say, air? Well, according to our rules, here's this light ray coming in, okay, and this would be the normal, right? And I didn't draw that straight at all, but that's supposed to be the normal. And basically, what it says is that if it's going into a slower medium, what is it going to do when it hits the normal boundary? Well, if it's going from a fast to a slow, it's going to bend towards the normal. Oh man, they can't see yellow at all, so let me just quickly change this real quickly. It's going to bend towards the normal. So instead of just going straight through this way, you can see that it's got a slight bend this way, and I don't know if you guys can see that laser line, but that is the laser line right there, okay? So it bent towards the normal. Now here, there's the normal again. It's going from a slow to a fast. Instead of continuing on its merry way this way, you can see there's a slight bend away from the normal, okay? And again, if those mnemonic devices are helpful to you at this boundary, we used FST, fast to slow, it goes towards the normal. And then here we have SFA, slow to fast, away from the normal. Okay, so that takes care of today's video. I'll see you guys next time.